All right, we're looking at a tougher example now for L'Hopital's rule. This is not one of your basic examples because when you first do direct substitution here, it's not quite in the appropriate um, indeterminate form, right? With L'Hopital's rule, you want to have 0 over 0 or infinity over infinity, plus or minus infinity over plus or minus infinity. Um, in this case, if you just think, plugging 0 in for the two x's or something a little to the right of 0, right? Because we're taking the limit as x approaches 0 from the right. And again, you want to be careful about notating this in the problem, but this piece alone, sine of x, will approach, sine of 0 is 0, right? So it'll approach 0 from the right. And then natural log of x as x approaches 0 from the right. If you picture the natural log of x parent function graph, it's going to approach negative infinity, right? We're on this part of the graph right here going down toward negative infinity. And so this is negative infinity. And that's not how L'Hopital's rule is set up. It's not for the 0 times infinity indeterminate form. However, that is an indeterminate form, right? Something getting really close to 0 multiplied by something that's getting infinitely large in magnitude. You don't really know just from that fact what that limit is. It's possible to have something getting very large, like this natural log of x, right? It's possible to have it growing in magnitude. Maybe by the time it gets to like around 10,000, right? Maybe the thing approaching 0 is much, much closer to 0. And, how do you compare like close to infinity versus close to 0? But you're really like comparing, because we're multiplying, we're kind of comparing the reciprocals. So the question is the reciprocal of this thing approaching 0, much more substantial than this thing approaching infinity? And, in this case, it would be. So like if you multiply these two together, you're going to get a small number. But on the other hand, if I add a bunch more nines here, right, just to make a really large number, now in this case, I have more digits here, so now this one would win, right? And it's kind of an informal way to think about it, but it's useful, I think, to understand why it's an indeterminate form. All that said, we're going to have to do something to this limit in order to be able to use L'Hopital's rule. So we have to think of a way to write it as a ratio, as a fraction, so that it's 0 over 0 or infinity over infinity. And I would advise, you can also see some of these where you might have like a 1 over x instead of a sine of x, or an x squared, or e to the negative x squared is another thing that might show up in one of these forms where you have things multiplied. Think of which one's easier to kind of turn into a fraction, right? You could change natural log of x into 1 over natural log of x, but that's more complicated, right? And I don't know that that'll help as much. Instead, in this case, sine of x is really easy to kind of take the reciprocal of, so it's in the denominator, because we have a trig function for that. And again, you can do this with another example. The number 45 in the same textbook is x cubed times e to the negative x squared, and it gives you it says x goes to infinity, so it gives you an infinity times 0 again. What you can do there is, since that's a negative exponent, is just move that to the denominator to get the correct sort of indeterminate form. Anyway, maybe we'll make another video of that one another time. Right now, for this, I want to rewrite this. I'm not using L'Hopital's rule yet. I'm just rewriting it algebraically. The limit as x approaches 0 from the right of, and again, the natural log of x, I'm just going to leave that alone on top. But what I'm going to do is take that sine of x and put it on the bottom. And so I'm just going to make it a cosecant of x. And now, if I do the direct substitution, the natural log of x as x approaches 0, that's still negative infinity, right? And the cosecant of x is, well, if you think sine of x goes to 0 from the right. So cosecant of x would be going to positive infinity. So now we're looking at a negative infinity over a positive infinity. And I'm going to show that work to justify using L'Hopital's rule. The way I like to show it is by writing the two limits separately. If you prefer, you could write a sentence: is of the indeterminate form negative infinity over positive infinity. And then you can use L'Hopital's rule just from there. So I'm showing the limit separately of the numerator and the denominator. And what I'm getting is, we already talked about this, for that numerator, as x approaches from the right, we're getting negative infinity. And for this one, we're getting positive infinity. Okay? And again, you don't want to write, don't do this. Or you don't want to leave it anyway. You don't want to write equals infinity over infinity, because that is not a thing, right? And if you're this actually has a value, this limit does, and if you write that it equals something that does not have a value, you have now written something that is incorrect, and you can lose points for that on, say, a free response question on the AP exam. So don't do that. Instead, break it up, numerator and denominator separately, show those limits, and now we can write equals, and I like to do this too, by L'Hopital's rule. It's worth taking the time to just be thorough, right? You have a little bit of time on the AP exam, for example, that doesn't take that long to do these problems. As long as they give you, you can write a little bit of a justification. So this limit equals the limit as x approaches 0 from the right of, and again, I'm kind of going from here, really. If you want to put the arrow from there, that's fine, but it doesn't really matter. I'm going to take the derivative of the top, and the derivative of natural log of x is 1 over x. And then the derivative of the bottom is negative cosecant of x cotangent of x. Got to know those trig derivative rules. And now, again, I don't really want to, it doesn't look that fun to plug that in with I got 1 over x on top, which I can already tell is infinity, right? And then the bottom, those are kind of nasty. I'm going to move the x to the denominator, right? I can do that. And while I'm doing that, I don't want to just leave nothing on top. I'd rather deal with the reciprocal functions for these trig functions. So that's what I'm going to do. I'm going to rewrite this limit. X approaches 0 from the right of, I'm going to put the x on the bottom. And on top, I'm going to take this cosecant of x and make it a sine of x. So negative sine of x. And then cotangent of x, I'll just make that tangent of x on top. Okay? And now I'm ready to think about direct substitution again. I kind of already thought about it a little bit over here, but now I'm thinking about it here. And what I see is sine of 0 is 0, tangent of 0 is 0, x is going to be 0. So 0 over 0 again. It's another indeterminate form. And you might think L'Hopital's rule failed me, but it did not. It's just not done yet, right? If we're getting 0 over 0, we can use L'Hopital's rule. So we can use it a second time. And the way I know it's going to work this time is because my denominator is just x. So when I take the derivative of that, it's going to be 1. And I'm not going to have that fraction anymore, depending on what happens on top. But again, you can kind of see that coming too. There's not going to really be a quotient from that. I mean, I guess you could argue that tangent and secant are quotients, but you'll see it's going to work out. All right. So again, show that work. The limit as x approaches 0 from the right of negative sine x tan x is 0. The limit as x approaches 0 from the right of x is 0. So both the numerator and the denominator are approaching 0 with those limits. Those limits are 0. And so it's that indeterminate form. And again, you could have just written is of the indeterminate form 0 over 0 here if you preferred. So now I'm going to kind of do the same thing again. Here, I'll leave a little more room on this arrow to write by L'Hopital's rule, so I don't have this ridiculously long equal sign. By L'Hopital's rule equals the limit as x approaches 0 from the right. And, hey, if you're working on this on your own, always a good idea. Pause it, work it out yourself first, and then see if you get the same thing as me. I'm going to do the bottom first. Derivative of x is 1. There, I did the hard part. Now you guys do the other part, right? On top, we have a product, sine of x times tangent of x. So we're going to do a product rule. Derivative of sine. I'm just going to put the negative on the outside and kind of open parentheses. You can do it however you want as long as you're consistent. Derivative of sine of x is cosine of x. Derivative then times tangent of x. plus, and then sine of x, remember I factored the negative out, so however you do it, just make sure you're doing it consistently. Either distribute the negative as you go or keep it factored out. Sine of x times the derivative of tangent of x, which is secant squared of x. And now I'm ready to look at this. And since there's no more like quotient here, I can actually write this as one limit now without a fraction. The limit as x approaches 0 from the right. And by the way, it's a sum also, right? They're two separate terms, so I can do those separately. I can take the limit of negative cosine of x tangent of x plus well, it's going to mean, I could just keep the negative. I could factor the negative out if I want, right? Let's make it minus the limit as x approaches 0 from the right of sine of x secant squared of x. And I think we're good to go now. And you didn't necessarily have to separate these. This is going to work out either way. But now if I plug 0 in, I get 1 times 0 with a negative there. So it's like negative 1 times 0, and then minus, and then here I'm getting 0, right? Sine of 0, 0. And then secant of x. Secant's 1 over cosine. So cosine of 0 is 1. So it's 1 over 1 squared. So it's going to be, the sine of x again was 0 times 1 squared, which anything times 0 is 0, obviously. So we get 0 minus 0 is 0. And that's the limit. It's just 0 is the end result